My mic is off. Speakers are on.
We're good to go.
This is good.
Okay.
I'm gonna need this. Yeah.
All right. Well, everyone, it's my pleasure to introduce Professor Jessie Runnoe from here at Vanderbilt. And Jessie's an expert on spectroscopic searches for supermassive black hole binaries. It's going to give us lots of information about that to see the electromagnetic view of finding these kinds of sources. Jessie, thank you very much.
Thanks, Steve. Hi, y'all. My plan for today is to tell you a little bit about how we do spectroscopic searches for binaries. And then I added a notebook to the GitHub so that you can practice a little bit how you might download Spectra, what the data model looks like, and do a couple of little tests. So we'll see how time splits up between these things. My background is actually in observations, multi-wavelength observations of quasars. So I come at this very much from the EM optical UV telescope side of things. That's the wrong computer. Cool. So the idea behind the EM searches is probably very near and dear to your hearts as well, which is we see, galaxies. Every galaxy we look in appears to have a central supermassive black hole, and we think that the way you build up cosmic structure is through this process of galaxy mergers and accretion. And so, a seemingly inevitable outcome of that picture is that you should end up with binaries, supermassive black hole binaries, modulo some evolution, right? There's a lot that goes on, and I think you heard about it today from Kelly and from Luke. Between a galaxy merger and the coalescence of two black holes. So this is just showing the time scale that a binary might spend with different separations. And I won't belabor this point because it sounds like you had a great introduction to it this morning. But one thing that is worth mentioning is that if you want to go and look for these in electromagnetic waves with light, different methods for doing that will tend to probe different parts of this diagram. So different techniques are sensitive basically to different separations. It's usually to do with the resolution of the different numbers. And I guess a useful number to have in your head is that here at about a parsec, there's a lot of uncertainty in the evolution and therefore the time that binaries spend at those separations. So if we could observe them there, that would be awesome, because the properties of the binaries we observe would help to nail down the evolution that's happening and how long it takes and so on and what the processes are. But at a pretty modest redshift of like 0.3, a parsec subtends like milliarcsecond scales. So that's the limit of what you can do with like radio. And so this is why we have so many different techniques for looking for them, because it's hard, basically. So on that topic, we're basically, I flipped it around. Now instead of going from white separations on the right, they're on the left. And here you have two galaxies approaching each other, and I'll just walk through pretty quickly different methods that you could use to look for binaries. And then today I'm just going to talk about one, and you'll hear from Maria this afternoon about another really popular and compelling method. So you may hear people talk about dual AGN or binary supermassive black holes, and the nomenclature is usually that dual AGN are not gravitationally bound yet, whereas a binary is. But they're very, very interesting because they're unambiguous signposts of galaxy mergers. And a way that we often look for galaxy mergers is with morphology of the galaxy, and that's kind of fiddly. So these dual AGN are very interesting in their own right, even though they're not bound yet. And they're hard to find because they're at the limit of what you can do with like an X-ray telescope like Chandra, because it has like a couple of arcsecond or a half an arcsecond resolution. So it's not as good as like a radio interferometer. if you go to closer separations, you can do radio interferometry about down to a parsec or so. It depends a little on the redshift. And there's a compelling candidate from this called CSO 402, and it's a seven parsec separation system, I think. So they see two flat spectrum radio cores. And here what you're trying to do is just use radio imaging to see two things, right? And flat spectrum usually means you're looking at an accreting black hole. In one of these latest papers, they actually see proper motion of the radio sources. And typically about 10 parsecs is where things get gravitationally bound, but it depends on the mass and the distribution of stars and gas and center precisely. And so I think the way that I think about that object, I'm not really like a deep radio astronomer, so I don't feel a lot of skepticism about it, but I haven't seen a compelling case that it must be gravitationally bound. So it's sort of right there on the cusp of being maybe a gravitationally bound supermassive black hole binary. In this regime, you're not talking, these sources wouldn't be bright gravitational wave sources yet at all, because they're not close enough. Below a parsec, there are many sort of indirect approaches to trying to find binaries. One is this radial velocity method, which is what I'll talk about. And this typically works. It's actually kind of a small part of parameter space in like right in the subparsec separation regime, corresponding to periods of decades at best, but maybe a few hundred years. So like longer than a grad student on time. And then the closer separation, like maybe milliparsec separations or so, you have a number of techniques. You can look for ripples in the line profile of iron K alpha in the X-rays. No one's done this yet because our X-ray telescopes don't have the energy resolution. You can look for a dip in the spectral energy distribution that comes from having removed some gas from the disk to stick the binary in there. So you're basically missing a segment of the temperature profile of the disk, and that shows up as a dip in the emission of that SED. That's hard to see because quasar spectral energy distributions have lots of shapes, have a lot of variety. And then a very compelling method is to use changes in the brightness of quasars and look for periodicities or quasi-periodicities, which is what Maria will talk about later. So these sort of indirect methods really are due to the challenge of finding these. Of course, if you could observe gravitational waves from them, that would be a direct detection, which would be great. So I'll talk about the radial velocity method. And in order to talk about this, you have to know a little bit more about the details of quasars and especially spectroscopy. So there are many papers that do it, and I've listed a lot of the important ones here if you want them later. But you may have seen this cartoon picture of a quasar. And in the AGN field, when you show this in a talk, they'll tell you this is a bad cartoon. But they won't tell you why. And actually, it was thinking about binaries that really brought it home for me. So the general picture, right, is you have a supermassive black hole, and somehow you have gas that gets down to it from the galaxy, and it forms an accretion disk. And the really important parts of this picture for thinking about finding binaries with the radial velocity method is that you have the central accretion disk and the broad emission line region. And then on really large size scales of like the host galaxy, you also emit narrow emission lines. There may be a jet. It's not really important for this. But the reason that this picture is a little bit challenging is that it deals with everything in these like concentric circles. And once you start, having two black holes in the picture, it's hard to decide where things go in that sense. So this is really a better picture of the broad line region. And the way that you can think about it is you have the accretion disk around the supermassive black hole. And the broad line region is really the outer part of that disk. And so you may have maybe this dense disk in the middle with a thin atmosphere. And the atmosphere could be like a disk wind that's lifted off the surface of the disk from radiation pressure that comes from the innermost part of the disk where the higher energy photons are produced. And we see from reverberation mapping that this gas tends to move pretty in like pretty Keplerian orbits. So not huge inflows, not huge outflows, but the dominant motion is basically orbital. It's a pretty flattened disk. We know that there in radio lab quasars, you can actually measure the orientation of the central engine. And you see an orientation dependence where if you look at things edge on, you see a lot of that motion. And as you get face on, the radial component goes away. And so you actually see signs of, fewer signs of the radial velocity. So it's predominantly disk-like. It's not floating clouds. It's continuous. This was really comes about because when you look at emission from the disk, it doesn't show up in like discrete bits. It's continuous, and so you can't have gas at discrete velocities to produce it. And in fact, in some quasars, we see clear signs of the disk in the shapes of their emission lines. So this is a better picture, and the reason that this is a better picture is that if you may have seen in thinking about supermassive black hole binaries that you have the two black holes in the middle and you have mini disks and maybe a circumbinary disk. And so that sort of concentric picture of having, accretion disk, broadline region, dusty torus, narrow line region doesn't work very well in that scenario. So this is a better picture to have in your head. I'm aware of the irony of saying it's a modern picture when like all the references are from the 90s. But it's a good picture to hold in your head. So how do we know all that? And what about spectroscopy? So these are images. On the left is star, and on the right is a quasar, which is where the name comes from, quasi-stellar radio source. And the challenge is if you look at these in imaging, you see none of that structure because the regions are very small and very distant. And so what you can do instead is, in imaging, you see none of those structures. In spectroscopy, everything that's sort of down in the central region will separate itself so you can see it. So if you look at this here, this is our quasar. And you can put a slit on it. And this is the way that spectroscopy works, is you use a slit or some kind of aperture. You can use fibers. And you point that at a CCD and you expose it and you take an image. So it'll look like this when you get the data from the telescope. And what you're seeing is you basically spread out the light with some disperser. So in this direction, you're seeing all different wavelengths. And then this is basically the spatial direction, so you're seeing along the slit. So you basically see an image of the slit at every wavelength. And so that bright source across the middle was the target, right? So it shows up in the middle of the slit, but at every wavelength. The vertical lines are emission. So the bright spots are emission lines from the target that we'll see later. And the vertical lines are the atmosphere. So it fills the slit, right? Like the slit was pointed through the atmosphere. So you see it along the entire spatial extent, and it emits light. And so you see that as those bright bands. So we would have to correct for that. And the way you can do it is basically just extract the brightness as a function of wavelength from the target and then from the sky next to it. And you'll get, yeah.
It looked like there was a positive gradient in the line.
Yeah.
I didn't understand why that would be.
It's just the optics of the telescope. You can get a drift so it doesn't fall into the pixels of the CCD like perfectly horizontal.
Oh.
So a big part of like extracting the data is characterizing that somehow so that it's not a part, like, you might take a perfectly horizontal line and like lose the trace of the object. So getting that tilt would be like a data reduction step. So once you have like the brightness at every wavelength of that central source plus the sky and just the sky, you can pull out a spectrum of your target. So this is a typical quasar spectrum. And in this sort of regime, actually the parts of a quasar really show themselves clearly. Here's the cartoon again, sorry. It's handy for this. So here is just another quasar spectrum. We're looking at how bright is the function of wavelengths in the optical. And here's a little cartoon of quasar just to keep you oriented. So there's kind of an underlying power law shape. And this is the sign of the accretion disk. So it's thermal emission, but the temperature, it's not one temperature, it's like hottest in the innermost part, and it cools as you go outwards. And so if you imagine lining up a bunch of black bodies, their peaks end up making this sort of power law shape. And the photons from this accretion disk will stream outwards, and they'll encounter gas in the broadline region, which you can think about as this outer part of the disk or disk wind, and they'll photoionize it. And for the most part, this gas is relatively dense, and its motion is Keplerian, so it's moving a lot. So the width of the line is Doppler broadened, and it's really indicative of the mass of the black hole. And in this area, you're still like really quite close to the supermassive black hole. Not in a GR sense, but on like a galaxy scale sense. Yeah.
To get that information, you need to know sort of how far away from the black hole you are that you're hitting that region.
Absolutely. Yeah, you do. And the way that we're able to do that is a technique called reverberation mapping. And it basically relies on the fact that quasars vary in brightness randomly. So if the continuum source gets brighter and dimmer, those photons will stream outwards, and a light travel time later, the broad lines will respond. And so if you map the brightnesses, you'll see basically, you can cross correlate the light curves and you'll see a time lag. And that corresponds to a distance. And an empirical result from that is that it seems to just scale with the flux. So if you have a big, like a lot of brightness in the continuum, you illuminate a lot of, like a large region, and you get a longer time. And if you have less, it's narrower. So yeah, that's a great point. You also see these narrow emission lines. They're also Doppler broadened, but the gas is distributed like throughout the host galaxy on large scales. So the potential, the gravitational potential is not so steep. The lines are not so broad. This will all be sort of key for looking for binaries. Okay. So the idea of the radial velocity technique for finding binaries is that you might, I mean, it works the same way that it does with stars, right? Like you're looking for, in a binary system, something's orbiting, it's emitting light. As it comes towards you, you should see a blue shift from that light. As it goes away, you should see a red shift. In the picture of a binary, we usually think about the primary being inactive, and the secondary being like an active quasar. They could both be active, and that's been thought about in a number of scenarios. But as that secondary is moving, that the broadline region is bound to it, and so it undergoes this bulk orbital motion. And so you can imagine then that relative to the narrow lines, which are emitted from the host and are moving, you should see successive like blue and red shifts of the broad lines. So this technique is just to look for that signature. And the challenge is really threefold. One thing is that this method is sensitive to a pretty narrow range of binaries, because you need it to be widely separated enough that you could fit the broadline region in there, but you need it to be close enough that the effect of the orbital motion is actually enough to measure. The other challenge is that the signature isn't unique. normal quasars can produce shifts in their lines, and I'll talk a little bit about that later. And then the last thing is not impossible, but a little bit tricky, which is that because we expect the period to be long, you're not going to see a sinusoid. The signal you look for is like a monotonic change in the offset. So you can imagine trying to pick a sample of binary candidates with this in mind. And this was done in a number of papers. The one that I worked with was Reckless-Held 2012. And what you do is you just go through the Sloan Digital Sky Survey and pick out quasars where you see really large velocity shifts of the broad lines relative to the narrow lines. So this is two examples. And the dashed line marks where the rest frame of the broad line should be based on the narrow emission lines from that host galaxy. And you can see a few things that are worth noticing. One is that when you see more than one emission line, they'll have the same shift, which is what you'd expect for like a bulk motion. But it's not what you expect for some weird things that can happen in quasars. Another thing is that you see both red shifts and blue shifts, which is nice because quasars tend to have outflows, which produce just blue shifts. And yeah, so those things are noteworthy. So the name of the game here basically is to monitor these spectroscopically, and you don't need to take really frequent spectra, because if you think the period's 100 years, going out every night is not going to help you at all. So what's really important actually is to build up a long time baseline. So we've been monitoring these for quite a while. We have these are distributions of how many spectra we have and what the rest frame time interval is that we're probing. And it's important to notice that because the first epoch of spectroscopy came from the Sloan Digital Sky Survey, which started in like 2000, we have a long time baseline now. We have covered a substantial fraction of what you might expect the period to be. And so you can build radial velocity curves. These are not all of the ones we've done, but there's some examples. And compared to what you're usually seeing for like sinusoids, they look kind of rough, right? Like this is hard to work with. But there are a few that look, that do exactly what you would expect if these were supermassive black hole binaries. So these are compelling, but what we really need is a longer time baseline. And the reason is that even in the face of the challenges that you encounter from not being able to see many cycles of an orbit, you can do some really interesting tests with spectroscopy. So, I mean, the punchline is what you can do is you can place limits on the mass and the separation the binary can have. And if you can place a limit on the mass, you can actually rule out the binary hypothesis that way. And so even without seeing many cycles, you can get a lot of information out of these. So the way that this works is you take a radial velocity curve. So this is just the observed velocity offset as a function of time. And you could describe that with the sinusoid. You should not, because of statistics, fit a line to that. But what you can do instead is basically explore the parameter space of this model. And at some level, by having observed some of the radial velocity curve, you've ruled out the shortest periods, right? If you assume that this doesn't oscillate among the data you've taken, and you're looking for long-term trends, you've basically constrained the period it can have. It must be longer than something. And so you can build a distribution of periods and find, okay, at some confidence level, the period must be longer than some number. And for unknown mass ratios and unknown inclinations, there's a phase angle and an inclination angle that you know nothing about. You can place a limit on the mass of the binary. And if that limit comes out to be something like, 10 to the 11, some mass bigger than anything we've ever seen, then you might say, okay, I have two scenarios. One is that I just found the most massive thing we've ever seen and the first binary we've ever seen, or this is not the model for these data, and this is not a binary. So this approach has been pretty successful with one type of quasar and showing that they're not really, the binary explanation is not a good explanation for them. In the case of these candidates, if you get a minimum mass of 10 to the 8, that's fine for a quasar. Many quasars have masses larger than that. And so the big difference is we really need a longer time baseline to sort of constrain the period that these could have better. So where is this going? We face a lot of the challenges that people who do photometric searches for binaries face, which is that quasars vary randomly, and so a lot of the sort of signatures we look for a binary can easily be confused with noise processes. And so radial velocity jitter is basically a noise process in quasars that we haven't measured yet. So you can imagine a radial velocity curve where you make some measurements for your binary and you're looking for a long-term trend, and it probably wouldn't surprise you if the data fall off your expectations here and there. And jitter is something that could cause that. It's a variety of random processes in an AGN that might cause the peak of the line to shift a little back and forth, but not for, not permanently or not for a long time. And so it just introduces noise. And so if we had a model for this, we could actually get much better constraints on the period, because this kind of effect really serves to inflate the error bars in your data in a way that we haven't accounted for. So one kind of jitter, we know it exists because we've observed it. So this is from our reverberation active campaign, like the technique I described earlier, where you just look at the brightness of H beta, so basically the area under the emission line curve. And then on the same time scales, how much does the peak of the line? And what you see is you can easily get, 100 kilometers per second of jitter in that line. That just comes from basically the continuum changes and the broad lines don't respond symmetrically to it. And so you induce a small change in the line profile as the brightness changes. And you can tell because it's related to the brightness. You can see the same structure in the flux curve and the radial velocity curve. So we know that this happens on timescales related to that reverberation timescale. And the light travel time there is usually weeks or months. And what we don't know is what happens on longer timescales. And that can be physically completely different. And the reason is that on the time it takes at light to travel from the central engine to the broadline region, that's much less than the dynamical time for gas to move in the broadline region. So you're basically, you can imagine like a flickering light illuminating a static disk of gas. And you can kind of get a view of what it looks like. If you wait a few years, then it can move. And so you can see changes in the profile that come from changes in the gas distribution. And so when we look for binaries, we're looking on timescales of years because we think the period is so long. And so we're subject to basically random noise processes or even systematic processes. You can imagine a spiral arm sort of processing around in a disk that would make a bright spot at some velocity that would then drift. Yeah.
Do you have some idea of what like the relative fluctuation of the density is of that gas on spatial scales?
Not well.
I suppose this would be how you might try to measure it.
Yeah, not well. We do see signs of these kinds of patterns, like you can make a model for a pattern like a spiral arm, and you can compare it to the line profiles that you get. And so that's actually part of this program is basically playing devil's advocate and saying, can we describe this with one? But you often don't know the density. We sort of write it as basically an emissivity, which is a combination of what it sees and how it responds to that light and what the density is. So that's We have some constraints. We know it's dense-ish enough to produce the line profiles, but the details of it are kind of hidden. That's a good question. So in a forward-looking sense, we now have the data to look at this, basically. So you've probably heard of Sloan, and you may have heard that the current iteration of Sloan, Sloan 5, is a time domain survey, and that's good for binaries. And the reason is not so much because it's going to monitor candidates, but because it's going to nail down these noise processes. So this is a distribution of how many spectra we had that probe different time intervals. And the blue histogram is just regular quasars from Sloan. You think of Sloan as doing like thousands or hundreds of thousands of quasars. This was a sample of like 200 quasars with like 2 spectra each. So it's not a big sample. And you can see in the hash histogram the distribution of the time intervals we're looking at with the binary candidates for the building their radial velocity curves. And it's systematically much longer. So we could see physical noise processes that we don't see in regular quasars. So we basically have no control sample yet. But I think I made this plot in like 2015, maybe. And so since then, Sloan has gotten onto this time domain kick and hugely is just going out and observing quasars. And so we've got now thousands of quasars on time scales and up into this 5 to 15 year range. So basically we have the data set to do it and to nail those things down now. So okay. So the radial velocity technique, I think, is very nice. It picks out good candidates. It's powerful because you can put limits on their masses. It's challenging because it's not a unique signature of a binary. But I think the outlook is good to make some progress on this just by studying normal quasars in modern time domain surveys. Okay. Do you have any questions? And if not, we can move on to some tutorial stuff.
Any questions online?
I guess I can look at that. I don't see any. Okay. So I think probably most of you are not going to do radial velocity searches for binaries as your career. But a realistic scenario, if you're interested in gravitational waves and multi-messenger detections, is that you might find some neat target or some candidate or something and you want to know more about it. And the spectroscopy is a great way to learn things like mass or the type of object you're looking at and so forth. And I think a thing that's often confusing is how do you navigate the big surveys and what on earth do they give you when you download files to try to do that. So if you look on GitHub, there is a tutorial and the aim of this tutorial is just to download a spectrum for a quasar and to correct for the effects of extinction in our galaxy. So the light from some extragalactic source has to travel through dust from our galaxy and it will be attenuated. And Sloan doesn't do any correction for that. And then similarly, obviously these galaxies and quasars are typically at cosmological redshifts. And so their emission lines appear at wavelengths much longer than they were emitted at. And you can correct for that as well if you can figure out where to dig out the redshift from a FITS file. So the tutorial will walk you through all of those things with a lot of links to more resources. And I can just share my screen one more time and kind of show you what we've got here. Oops. Okay, so you can get this from GitHub, and you will need a couple of packages, which you may or may not have, depending on how much survey astronomy or EM astronomy you've done before. AstroPi has many, many tools for doing, astronomy stuff. So it's handy. And the other two packages are for handling extinction corrections. So this is all pretty self-explanatory. There's a section here on the Sloan Digital Sky System. So I guess a useful piece of information to have is that Sloan doesn't organize its spectra by RA and DEC, which would be great. It organizes them by unique identifiers of the spectra. So MJD plate fiber. So it's basically when was it taken, what was the plate number, and then what fiber number plugged into it. And so sort of a key idea of this is you have to have some way of going between RA and DEC for a target. I've given you an RA DEC for a quasar, and MJD plate fiber for any spectra. There might be more than one that exist for it. And there are a number of ways to do that, which you might choose depending on if you're just trying to look around and understand what's going on, then sort of an interactive web app would be great. If you have to do this for 5,000 objects, then doing everything in Python would be great. So there are a couple of different avenues you could choose. Since we're just doing one today, we'll sort of pick the easiest option. But if this feels really easy to you, you could try to automate it and make yourself a Python tool so that you plug in an RA DEC and it downloads a spectrum for you, which can be done. So let's see. So I've given you links to where they store. So all the Sloan spectra are just stored on the internet, and you can go navigate around. It's just hard to tell what you're looking at because it's all listed by like plate and stuff. But if you're trying to generate automatic commands to download them, you can go look at what you're doing and see like, is the thing I'm trying to download there? It looks like this. There's just lists. It's also slow. Lists of plates with spectra. So you could go and just click the thing you want if you could find it. But having tools to look for what you're trying to download would be like a little more helpful, right? Enter the navigate page. This is a handy page. You can put in an RA and DEC here. And then if you click explore, it will take you to a page for the object you clicked. And it has all kinds of information for it, including a list of the spectra that exist. And you could pick one. And if you click fits, it will give you a download, and this will just automatically generate the link to that last page and automatically download it for you. You could also write this in a Python script if you were so inclined. But what we'll do today is just enter the RA DEC for this object and download a spectrum this way. Once you have the data, you can write in, you'll see the file name you downloaded, you can write it in. And you have to open it. So Sloan stores things as FITS files. If you haven't seen these, they're basically stacks of data, and each layer has a header of information and then data. And so I've given you some tools to kind of look around in the data that you download and try to find things. So you could separate the header and the data and then extract the wavelength and flux for a spectrum. And then you also have to find, it'll store a pipeline redshift in there, which you can extract as well. There are some links. The data model will tell you what comes in the file. So you can look that up. And if you haven't done anything with FITS files before, there's a link here that shows you a little bit about like, how do I open one and so on. Correcting galactic extinction is basically a matter of downloading dust maps. So you can pull those off with Git. I've given you the link. And then you just need to know, like, where am I looking? And it'll return how much dust is along the line of sight. And then you can translate that into basically how many magnitudes of extinction does that create in the V band? And then use a dust law to tell you, okay, and then how many magnitudes of extinction at any other wavelength. And correct your whole spectrum. And then redshift correction is divide by 1. So you guys are welcome to work through these tasks. And I can help if anyone gets stuck. And if you have done this sort of thing before, or this feels not very difficult, there are some suggestions at the end. Really a nice thing to have is a function that if you give it an RA and dec, you don't have to go and manually click on a web page to download a spectrum, and it will automatically just do it for you. So building something like that is also a very useful exercise. Yeah. What was that?
Which filter do you want to use? One in particular?
So if you, so it's got fixed in a couple of.
Oh,
You
this
actually
one
want
was,
spectrum.
oh.
They will actually also give you the bits files for the images for the,
Okay.
to be targeting.
How much more complicated does a production level pipeline look like? Is this sort of like a still version of it, or?
This is in some sense the first steps. It really, you do have to have some way to like translate RA dec to the identifying information for the spectrum. And the reason that's hard is because they store it in 2 places. And you have to know which one, like there's like old data and new data. And so you have to know which one to grab. And so just a switch, but you have to get that somehow. No one ever saves it. So you can do like an SQL query. Actually, most automatic large scale.
Is it just like bouncing between these sources?
Yeah,
It's not here, it's go here.
Yeah, that's what I do. I just run one and then whatever fails, I'll run again. But in preparing for this, I was felt motivated and wrote like an automatic one. So it's not much harder. I can show you what I wrote. You basically need a function to just go to the website that has the SQL query. And you have to figure out what query to write to grab things. And this will do it object by object, which is kind of a drag. You could also, if you had everything in like an area, just grab all the data in that area. So that step is kind of a pain. And this will basically get you data that are ready to analyze, but it does no analysis. And that part of the pipeline is the big thing. And it's a wheel that everyone reinvents because no one is satisfied with the way that anyone else does it. Um, yeah. The main trick is basically for the purpose of doing this kind of thing. All of this is noise and you just want to isolate this. That's the trick.
What's the incident that part?
So. It's up here somewhere. The DAT part. So the FITS files are split into, so when you open them, you get like what's called a header data unit. So it's basically like a stack. And it will have some mysterious number of extensions that you won't know when you open it. And each extension has a header section and a data section. And so the header in that is just meant to be the header section and the data section for the extension that pulls the spectrum, which in this case is the first one. And a useful way to figure it out is if you put hmu.info, it will tell you how many extensions it has and what is in them, and a bunch of junk out data types.
How
So
do I
you
know
can
if it's in the first one?
a more useful way would be to grab the header. And if you print the header, it will tell you the names of all the columns that are in there. And columns like flux and log lambda are maybe a little bit of a giveaway. There is also this data model. If you click that link up there, it describes what all the extensions are and what all the columns are, and so you can go look. But indeed, I would argue that figuring all of this out is one of the most. And anytime you would use any survey, you have to figure it out again. And it's hard. So in this case, you can find it described in this data model, but the spectrum is in the 1 extension and the redshift is in the 2 extension.
And does the header contain? So like, it looks like you call that log lamb. If I just print out like HDR,
Yeah.
I don't, like I see log lamb, but it's all lowercase, like here.
Oh, yeah.
Is there a way to know like what I can call within?
It should let you do lowercase log lamb. So if you do, I think that will work. Yeah. You would think it would complain about caps, but in this case, it does not. And the way to figure out, so I can show you what this looks like. So it'll tell you here what's in the extensions. And it'll tell you, okay, here's the flux. This is the 1 extension. They called it coad. What are the units, for example? It's a thing you'd like to know. So you can come here to find units. You can also this spec obj thing describes what's in the 2 extension, and probably useful for you guys is this best redshift parameter. So they measure redshifts like a whole bunch of different ways. They'll do something like, assume this isn't a quasar, what redshift do you get? Assume it is a quasar, what redshift do you get? Things like that. And then at the end, they decide what the best one is. And so that would be a sensible thing to use. They're not good 100% of the time, but they're usually pretty good. To get wavelength, I think is pretty self-explanatory from log lamb. flux is flux, that's great.
What log 10, what log-
It is log 10, good question.
Is it to you, extra?
The uncertainty is maybe not obvious. So there's a parameter called IVAR, which is basically the like 1 sigma errors are 1 over the square root of that thing. It should look like this. One subtle thing about plotting spectra that I notice people don't do is, in fact, you should plot it basically as a histogram. Because you can imagine you didn't measure the flux at like literally every wavelength, you measured some specific wavelengths. And you know there's basically some flux in that bin. So you can do that with this like draw style steps mid. In something that's this high resolution, you don't really see the difference. But in fact, it's a more correct way of doing it. And spectroscopists will appreciate it. Yeah. So the dust maps are just a bunch of FITS files that basically have a grid in the galaxy of E, B minus V, so the color excess that you produce from dust at all different positions. And they measured that from like absorption lines. So the Hubble Space Telescope did a lot of work on this. They look at absorption lines to try to characterize how much dust along different sight lines. So to do the extinction correction, you're basically just going through these steps one by one. Were folks able to get the dust maps okay? Yeah. So you can just load up a map like this. And then query it for your position and it'll return an EB minus V value. And typically for the Milky Way, we assume that those are related by a factor of 3.1. So this correction is only for dust in the Milky Way. If there's dust in the host galaxy of the quasar you're looking at, there could still be reddening effects, which you haven't corrected for. And the reason that's challenging to do is because you don't know things like, how are extinction and reddening related in that galaxy? And in fact, in some other galaxies, we see other numbers besides 3.1. But for our galaxy, it's relatively well characterized. So you can at least correct that effect. So you can figure out, okay, this is magnitudes of extinction in V. And a dust law will basically, I think this has some plots. Maybe, yeah. A dust law basically tells you if you have some amount of extinction in V, what extinction does that imply at some other wavelength where you actually want to make this correction? And there are different shapes for these. And they have to do with things like the composition of the dust, the size of the dust grains. This 2175 extra bump. I can't remember what the heck it is for why that's there. Maybe it's still a big mystery. But in practice for the Milky Way, you can use this Fitzpatrick one that will be fine. There are some applications where this choice is a very important choice, but this is probably not one of those. So you can then just calculate, given V, AV, so some normalization for that curve. What's the extinction of every wavelength in your wavelength array? And then just apply that to your fluxes, the way that fluxes and magnitudes are normally related. And you should find when you plot it that it gets brighter. And it may not always, this is actually kind of a good change, but sometimes it's not so much. Yeah, what's up?
What does this mean? RD equals AB divided by EB minus.
So this is, just how the,
What are the letters?
yeah, so EB minus V is, called the color excess. So it's basically, the observed B band magnitude minus V band magnitude.
What units does it have?
Magnitudes. So B minus V has units of magnitude. How are we gonna get this to go up? Yeah. No. I'll take that one. Can I get you to erase these? Okay.
Yeah. Just watch your head there, Jesse. It's coming down on the side.
So, okay.
Is E a function or is it a area?
Neither. Which is really confusing. So it's, I'll explain this in just a second. Okay. So it's really this. So in this case, B and V are magnitudes in the B band and the B band. So you're basically what you're doing.
I'm so sorry. What is a magnitude? Doesn't have units.
It does, it's units of, like, that is the unit of magnitude, it's basically like a log flux. It's basically like a log flux.
It's a log of power per area.
Yeah, so it's like energy per second per area. And usually per, like, either per frequency or per wavelength.
What does a period?
This
Yeah.
is a zero. So
Oh,
basically what you're doing, if this is the flux versus wavelength, so this is like a spectrum. You're probing its shape when you do this. So if you have something that looks like this, you could put it in log scale. And there's a factor of 2.5, you ultimately you get these kinds of magnitudes, but it's basically like if you take the brightness of the source, like shining, and all of that light comes in all directions, and eventually some of it. So it's basically energy per second that it's putting out per area. But you might observe it with a filter, so you're observing like only certain wavelengths, so that basically counts for that. So energy per second per area that you observe in like the V band specifically, or shorter wavelength, the V band. So it's like brightness, log brightness in V and log brightness in B. And the difference basically tells you the shape of that spectrum. And dust will make spectrum redder because it will preferentially absorb or scatter over light. And so this is basically what is the color of the spectrum? And we use color to mean basically its slope or its shape. So how, if it's really got lots of power at short wavelengths, we call it blue. If it's less power at short wavelengths, we call it red. So what is the color intrinsically? So that's the knot. So what was it supposed to look like? But what does it actually look like? And we call that the color excess, which we just
Where do I
write.
get what it was supposed to look like.
And so that's the challenge. And we basically, if you look at absorption lines along the line of sight. And so you can see the effect of the dust very specifically there, and they model like the depths and profiles of these absorption lines. And figure out how much dust is along the line of sight and what it's doing to the light. So this is a whole field of astronomy, and what they produce is a map. that basically tells you this value of the positions based on what they studied about us.
Is E B minus B something that lives in the SGS?
So that is what you get from the dust.
Okay.
So the dust map is literally
That's
like,
probably what E B.
yes. So the dust map is literally like a map of our galaxy. And you have like positions. And you can put it in, RA and deck, or you could put it in galactic coordinates, which might also make sense. And you say, oh, okay, my source is there at this RA and deck. And so you go into the map and you get that value, and it tells you this EB minus E. And so that's basically what was the effect of the dust. What was, how much did it change the look of your spectrum? And
Doesn't it depend on how far away it is?
it doesn't really, because we basically have just looked and built this empirical map of what the effect of dust is along every line of sight out of the galaxy.
It's just all of us.
It's only our galaxy. Yeah. So distance may make many opportunities, more opportunities to do other deaths along the line of sight, and this will not correct that. And in fact, a really obvious place for there to be more dust is in the other galaxies that you're looking at. And some quasars look very red. And we don't know because we haven't done these deep absorption line studies of what's going on in that dust. We don't know how to do this very much harder. And so you have to assume many things. So these are good questions. So if you get this B minus V, that basically tells you how the shape of it should have changed, but it doesn't tell you like an absolute amount. At some way, like how much does it get stomped down, right? And so that's what the AV basically is. So it's how much kind of like a log forest, but it's like how much extinction was there just in the V band. So basically, how much brightness is that using? But you have a spectrum at many, many wavelengths, and so it's not just one filter. You want to know you have some wavelength array that you grab from the sun. You want to know the extinction specifically at those wavelengths, and so we would call that, like a lambda. For any lambda, you can get anywhere. And so that those dust laws basically translate to say, okay, if you have this much in V, it implies this other amount. And the way that that is determined is basically by details of like, what's the grain size? What are the grains made out of? What do their surfaces look like? And so there are different dust laws. And I've directed to the one that's pretty good. But if this is one of the reasons it's hard to do another analysis, because you don't know what's going to fit in that case. This relationship you asked about, what is like AV over EV minus V equals is 3.1. And that's just how do you get from here to here? And in the Milky Way, yeah, we find that these appear to be related by 3.1. In the Magellanic Clouds, it's like 2.7. So it just changes sort of what you said. How do you know what the dust does? Because we see that this is what it does, but in many cases we don't always. Yeah.
Just, I guess this is more of a curiosity, because I've seen the 3.1 before, but not really know too much about it.
Yeah.
How old does that actually hold, regardless of like which direction you're looking?
That's a good question, and I don't know a detailed answer. I think it's pretty good in our galaxy. So the direction I think is okay. But it certainly is the case that in other even nearby galaxies, we really remember, and we're sort of helped along by the fact that a place I imagine would make a bigger difference would be like alongside lines that go towards the center of the galaxy, where there's much more dust. And we don't do extragalactic surveys there because you can't see anything here. So most of our extragalactic surveys like point out of the plane of disk because it's easiest to do, right? So it's a good question. It's a good question.
Very different question. Just out of curiosity, what's the steps to
Let me zoom in. It makes it into a little histogram.
Oh, really?
Yeah. So. Oh. There she is. What do I call it? Oh. I'm on the wrong computer. If you just zoom in, what you'll see is it's basically when you're plotting the spectrum, right, you have like wavelength and flux, but you don't actually observe literally every wavelength to make it a continuous thing, right? So you'll have like things like this, and you might have an emission line, right? And if you just plot it, it will connect the dots. But that's not really accurate because technically you're observing in like wavelength bins. And you don't know that, oh, this side of this bin has a larger flux than that side of the bin. And so the most fair thing to do would just give it the flat top and say, in this wavelength bin, I measured this value. And the steps bin will do that. And if you zoom in, you have like a purple spectrum with not a lot of data points, you can see it very clearly. Yeah. Okay. Probably
We should
probably about time, huh?
call it in about 5 or 10 minutes.
Okay.
Actually, you're right. We should.
I think it's about
We
time.
should wrap up. Yeah.
I give you a notebook with all of my, like a solution notebook, so you can just follow it through. And what this will basically give you is a spectrum that you then could do science on, because you've corrected for the extinction that you know is happening, because it's in our galaxy and you know it's there. And you've put it at the rest frame of the quasars, and removed, the effective cosmic expansion. And so this you could do analysis. If you wanted to do something like measure a black hole mass, now you're ready. Which is probably one of the most, the things you would most want to do, I think, for quasar spectrum. And similarly, you can do the same kind of extinction correction on like magnitudes that you download from brightness surveys that show the brightness. Cool.
Yeah. Thanks so much, Jessie.
Yeah. Okay.
Okay, let's take 10 and then Maria will take over Okay, everyone, to round out the electromagnetic view of supermassive black hole binaries, allow me to introduce Dr. Maria Charisi, who's a postdoctoral fellow here. Maria is an expert on photometric searches for supermassive black hole binaries and was one of the pioneers doing this in time domain surveys, particularly PTA. And Maria is now going to tell us about what these kind of searches can find and how we can maybe dovetail these with gravitational wave searches.
Yeah, thanks, Steve. So I'm going to talk about the other broad popular method compared to spectroscopic searches that Jessie just mentioned. And some of the introduction will be similar to what you saw already and what you know. So, of course, all of you know that supermassive black hole binaries are the natural outcome of galaxy mergers, since every massive galaxy should have a supermassive black hole in the center. So when the two galaxies merge, we have the two black holes in the post-merger galaxy, which progressively lose energy and angular momentum, and they orbit at smaller and smaller separations. The important part of this story is that galaxies typically have gas, and that gas is perturbed, and most of the times it gets to the center of the post-merger galaxy. And when that falls to the black holes, that produces the bright emission that we can use to detect these systems. And you can see that the galaxy merger typically takes a long time to complete. And this was a merger of two spiral galaxies. Even if we have the merger of two, let's say, elliptical galaxies, which are more massive, the elliptical galaxies are not very gas-rich, but they still have some gas. So we do expect that the process of the merger will bring this quantity of gas in the center and allow us to detect bright emission. So Jessie already mentioned that we have a lot of information about the initial stages of galaxy mergers. When the galaxies start to interact and tidally deform each other, we have tons of images like that. We also have, and this is actually the last decade or so, we have seen a few dozen of galaxies that are dual AGN. So these have two supermassive black holes, you can see here, that both are active and they are separated by some kiloparsecs. And these can be resolved in a variety of wavelengths, X-rays, infrared, radio. A lot of the telescopes, I think this is from Hubble. A lot of the telescopes have the resolution to find these galaxies that have two supermassive black holes at the kiloparsec scale. It's not super easy, but it's easier than from the parsec and below. When we go to the parsec scale, again, Jessie mentioned this exceptional candidate that we have The only technique you can use and has enough resolution to image the two black holes is the very long baseline interferometry. So practically you know it from the Event Horizon Telescope. You use the entire Earth as your telescope. And this is the record holding binary here that Jessie mentioned before. It's separated at 7 parsec. It's at the edge of being a Keplerian binary, practically being gravitationally bound, the one black hole to the other. So this is the one binary we think we confidently know so far. If we go to smaller and smaller separations, then even that technique doesn't work. Jessie mentioned that we need smaller than milliarc second resolution, which we don't have. So what we need is, we need to infer the presence of the binary from the effect the orbital motion of the binary has on the environment, and in particular on the gas that we think should be in the center of the galaxy. And Jessie already mentioned the technique that works at the larger separations, sub-parsec. The technique I will talk about covers a little more of the parameter space and can go down to the milliparsec regime, which is where gravitational waves are emitted. And it's the one that we can very easily combine with pulsar time array data to do multi-messenger observations. And at the end of this presentation, I have some ideas of how we can go about combining electromagnetic data with pulsar time array data. So how do we find these systems? We need to look for quasars with periodic variability. So why quasars? We think that at least some of the quasars are associated with galaxy mergers. As I said, the process of the merger perturbs the gas distribution and brings it to the center, which then it accretes to the black holes and produces this bright emission. And you may have mentioned to you in his talk whether quasars are the best places to look for binaries, if all of them are associated or a fraction of them, and so on. But in general, we think that quasars should be a good place to start. And why periodic variability? I would say this is fairly intuitive. If you have a binary that is moving periodically and you have gas, you will have periodic perturbations of the gas, and somehow they will be translated to periodic changes in the brightness of the system. But this has been studied extensively with hydrodynamical simulations. And what we typically see is when we start with a disk of gas and we put a binary that is orbiting around. So what happens is the binary in the center acts as a propeller and expels the gas from the center. So we have the creation of this cavity, the dark part here. So we have low density gas there. The good news is that this cavity is not completely devoid of gas. So there is some gas that penetrates this cavity, and that allows us to get this bright emission. So if you notice here, we have periodically these streams coming in, and they hit the black holes. So if we look at the rate that these black holes are fed as a function of the binary orbit, we see a periodic pattern. Here, the green is the feeding rate to the smaller black hole, the secondary. The blue is the feeding rate at the bigger black hole, the primary. And you see that the secondary is getting most of the gas, just because it orbits closer to the edge of the cavity, so it can pull the gas inwards. And then if we take a periodogram, you see a strong peak in the accretion rate at the orbital period of the binary. So what these simulations show us is, first of all, when we have this process of the gas falling onto the black hole, that can produce bright emission that resembles a quasar. And also the brightness of these sources should change periodically over time. Another thing we see very often in the simulations is that the systems at this stage evolve very slowly. That means that they spend a lot of time in these sub-parsec separations. And since they spend a lot of time, they should be very common and we should be finding many of those. And indeed, the last 5 years have been very productive. And the reason is that we have these time domain surveys that systematically scan the sky and record the brightness of different objects again and again. And this is how the Palomar Transient Factory covered the sky over the course of 4 years of operations. And you can see that some of the fields at the end of the 4 years, they have even thousands of data points. So this was actually this time domain survey, PTF, and many others gave us a lot of nice light curves to actually start doing the periodicity searches. Actually, my thesis was one of the first studies to systematically search for this type of systems. This is actually a very productive field. This slide is already outdated because there was a paper a couple of weeks ago that found another 100 candidates. But now we have about, let's say, 250 candidates. And these are candidates for being quasars that vary periodically. And if they are indeed quasars that vary periodically, they're candidates for being supermassive black holes. So I repeat a lot the word candidates because finding quasar periodicity, it's actually harder than it sounds. When I started discussing my thesis project with my advisor, I was thinking, okay, that's a summer project. We'll do it in 4 months and we will be done. And if it works, that's perfect. It took us 18 months to write the first paper, and it's 10 years later, and we still don't have a confirmed binary. So that can show you how hard it is to find quasar periodicity. Some of the reasons, you can already see them from here, from the data. You can see that the data are relatively sparse. They have gaps. And in some cases, the gaps are very large. They have, and one, I guess, a really significant limitation is the periods we are looking for are relatively long. That means that we cannot observe multiple cycles. And again, that means we cannot very easily confirm the periodicity of the sources. So you can see that in most cases, we have maybe 2, maybe 3 cycles. And the quality of the data is rather limited. Another reason this is very complicated, and it's not obvious here, is because quasars have stochastic variability, which can mimic this periodic behavior that we are looking for. And all of the searches that I showed you and the candidates, they used some model to describe the stochastic variability of quasars. But still, because we have very limited baselines, it's very easy to confuse the two. So here you see the data of one of the candidates, and you can see they fit very well with the sinusoidal model. And the pink below is just normal quasar variability, and in the limit of this 10 years of data that we have, both can be fit with the sinusoid. So this is an intrinsic problem. It's not like we are doing the statistics in a wrong way. It's that we don't have enough information to tell the two models apart. So because this is a gravitational wave school, I thought I would mention another thing. We think a lot of these detections from these 250 candidates are probably false detections. And the reason is that individually, they are not strong enough to be detected as gravitational waves by pulsar time arrays. But as a population, they contribute to the background. And Alberto Cesana here modeled this background that we would expect if all the candidates we have recognized in the time domain surveys were indeed binaries. Of course, this is a theoretical model. There are assumptions about the mass ratio, about even the mass of the candidates, and so on. So based on the most optimistic model, we would be up here, and that would be in tension with the limits we have from pulsar time arrays. If you go to a more moderate model, we have moderate tension with gravitational wave background. But this is another indication why we expect that some of these samples are contaminated with false positives. Now, of course, how can we confirm or disprove that some of these binaries are good sources or bad sources? One way is to look long enough. I mentioned that the periods are a few years. So if we have a period of 5 years and we want to see 10 cycles, we need to wait 50 years. It's long. It's not as long as the time scales Jessie was describing. But we can also do other stuff in the meantime. And I will mention just a few of those very briefly. And the thing is, we can collect other type of information and see if there are additional signatures that could, let's say, lead to convergence of evidence that these candidates are binaries. So one is this idea of the relativistic Doppler boost. So if the observed period if the period we're observing is the orbital period of the binary, then the black holes orbit with relativistic velocities, just a few % of the speed of light. And as I said, typically the smaller one, which is the one moving closer to the edge of the cavity, it's brighter. And similar to what Jessie was describing, when this small bright one is moving towards us, it will appear brighter, even if in the rest frame, the luminosity is constant, just from conservation of photons. When it's moving towards us, it will appear brighter. When it's moving away, it will appear dimmer. And that gives rise to a quasi-sinusoidal periodicity. And also there's a very good prediction that if you take the spectrum that Jessie was showing you, and you look at different parts of the spectrum, for example, at the optical and the UV, these typically have different spectral indices, so the slope is slightly different. And that means that the amplitude of the light curve should be different. So if you have optical and UV data, they should vary simultaneously, but they should have a different amplitude, which is predictable from the spectrum. So I will just show you one example of this. So the top is the optical light curve, and the blue line is the fit to the Doppler model. And then the bottom, the blue line is a prediction of the Doppler model of how this light curve should look in UV. And here are UV data that we took with Swift, and you see they fit the prediction very well. But of course, this is not the entire story. This is a good candidate. It is consistent with Doppler boost, but quasars also do that. And you can see that the light curve here in the UV is very sparse. We have like 10 data points. So in the limit of this sparse data, we can confuse the signature with the variability of quasars. So there's a lot of work that is ongoing to uncover these additional signatures. One is taking spectra to just look at shifts exactly the way Jessie was describing, even though we don't expect these methods to work in this regime. This is some work we did with Joe Simon that talked yesterday, because we were at Caltech and we had access at Palomar. So that was the main reason. Another potential signature is that we expect to have multiple components in the periodicity. So I'll just spend 1 minute here because I put it in the notebook that I put in the GitHub. So there's this idea that as you have this dynamic interplay between the binary and the accretion disk, we have the component, the periodic component of the orbital period, but sometimes we have the formation of hotspot at the edge of the cavity. And that moves slower than the binary, again, Keplerian orbits. So that will take 5 or 8 times to complete the orbit around the cavity. And that could also be another contribution for a periodic component. It's hard to detect this signature for, I think, reasons that will become very obvious once I get to the notebook. But this is also another signature that we can search. And of course, we are working across the electromagnetic spectrum. We have taken X-ray data, UV, every telescope we could get our hands on, just to look how these sources behave in different wavelengths. Now, this is a very exciting time because, okay, the time domain surveys we had this decade were great, but they were the first surveys. We will have this amazing survey, which is the legacy survey of space and time of the Vera Rubin Observatory. And this is an image from last winter. You can see that the dome, the construction, is almost complete. We expect that LSST will start taking data in a year. And actually, I think it will be on time. It had a delay because of COVID, but now we are on track. And in 2025, we will have the first data release. So LSST is amazing because it will have very good quality of data. It will see much deeper than the current time domain surveys. That means that we will have samples that are at least 2 orders of magnitude bigger. And in that case, we expect to see even the rare things. And the rare things are the ones that have short periods. Again, if you remember how binaries evolve, they stay at the large separations for a longer time. So we should expect to see many of them that have periods of a few years. As I said, these are very hard to detect. But also in these huge samples, we should expect some that have periods of a few months. And if we have a binary that has a period of 6 months, let's say, over the course of LSST, we can see 20 cycles. And that's good enough to convince us that this source is periodic and it is indeed a binary. There's a lot of predictions of how many such binaries we should see in LSST. And uncertainty is related to what Andrew is doing, how many quasars host supermassive black hole binaries. So until we have LSST data and we do these searches, or the theories come up with better models, we won't know exactly how many we expect, but we definitely expect many more than what we have now. So in preparation for that, we ran some simulations and we developed a method for detecting this periodicity in LSST. And that was work led by Caitlin Witt, which I think many of you know from Nanograph. So we looked at, by simulating realistic quasar noise and simulating realistic binary signals, how many we would detect, how many we would miss, and how many we would falsely classify as binary candidates when it's just noise. So what we see is that both, so this is the ROC curve, so the false positive rate, real things that we miss versus the true positive rate, true things that we detect. And what we see is like in both current time domain surveys like Catalina and LSST, our ability to detect these periodic signals is about 60%. The 40%, we will miss them because the noise is complicated and it's hard to distinguish them from this dumb random walk noise. The very interesting thing is like here we go from false detections at the rate of 15 to 20% to something that is close to 0 point something percent. So the false detections in LSST will be at a much lower rate just because we have better quality data. So this is very exciting because if we had a lot of false positives in LSST, we will just be flooded by false positives just because the size is so large. And I think this is really good news. I can take a small break before I go to multi-messenger stuff to see just if you have any questions on the EM part.
So how many different binaries do you have through various week?
0. All of them are candidates. I would say there is one that I didn't mention here. It's called OJ287. So this is a bright source, a bright blazer, and it has been observed for 100 years or more. And this has a periodicity of 12 years. And we see the flares repeating every 12 years. The last 50 years, the light curve is very well sampled. So I think there's a lot of confidence that this one is a candidate, but you see, it's like 12 years. We still don't have quite like 10 periods, but we're getting there.
Microsoft does have some really good models that back up for the James Wade stuff. Really close, like a binary match is really close to.
Right. So there are predictions that can predict the arrival of the flare within a few days. I would say the models, and I think someone here is involved in that modeling.
Like a slide.
Yeah. I think there are a lot of parameters that go into this modeling. So maybe by turning the knobs, you can get the correct model predictions, but I think OJ287 is a really good candidate. It didn't come from this time domain surveys. It just happened that we have a bright source that we have been observing for a very long time. So still a candidate.
Do you need like a certain number of periods to confirm that it's binary?
That's a hard question to answer. I think the more cycles you see, the more confident you become. But because I will talk about multi-messenger observations, if you happen to have a gravitational wave signal with the same frequency from the same part of the sky, I think then you can start also building your confidence.
What is the expected strain on that one?
I don't think it's
We
that.
don't-
So I think it is a massive one. It's a low mass ratio. So the primary is 10 to the 10. The secondary is 10 to the 8. And it's also in a high eccentricity orbit. So both the mass ratio and the eccentricity don't help us with the strain.
It's like
Maria, do you have any opinions about, say, recent talking with the binary?
So the TikTok binary, for those of you who don't know about this candidate, there was a quasar that shows a chirping signal. So it has this periodicity, but the frequency is going up, similar to what you expect when you have gravitational waves. And they claim they saw 6 or 7 cycles of that, and that it was a binary in a very eccentric orbit. The probability of finding something like that is very, very low. I mean, this was extremely eccentric, almost unbound. And I think there is a recent paper by the group in Milan that looked at, they have more data, follow-up observations, and it doesn't do what we expected if it was a binary. So I think we can already exclude it. There were more arguments why you could exclude that. And there is, I think, a paper from a graduate student who is working with CTF data. This is a double peak emitter, which It's one of these classes that initially they thought it's a binary because it has these two peaks. Now this model is disfavored, and there are more in the ZTF database that do this chirping behavior. So I think it's a class of AGN variability that it's at the edge of the parameter space and we haven't explored that much. It's very unlikely to be a binary.
I think Jessie has some time as well to look at it.
All right, Jessie got time on Hubble to take spectra, UV and optical spectra. Yeah. Okay, so I can spend a few minutes, but I don't know how I'm doing with time. Just to discuss what are the opportunities of combining electromagnetic data with pulsar time array data. So the interesting part about this is that both my methods that I've been describing, both the EM emission, this periodic variability, and the PTA, they probe the same population of binaries. So similar masses, similar periods. So it makes sense that we try to put them together for many reasons, because we can make the searches more sensitive. We can have better parameter estimation. We can increase our confidence for a binary. We can uncover complementary physics just by doing the two messengers together. So we looked at different models and we found that the relativistic Doppler boost that I was describing is the most promising to combine with PTA data, just because you can connect all the quantities of the binary. You can connect the period, you can connect the phase with the gravitational wave, you have information about the inclination and the mass ratio. So this is probably the maximum information you can get and combine it with gravitational waves. And this is how a binary, let's say, would look if you looked at the time residuals. So for those of you who have thought about time residuals of individually resolved binaries, this is the Earth term only. So you see a very clear sinusoid. And this is how the electromagnetic signal would look like. And you can see that we can very easily connect the two. The gravitational wave signal has twice the frequency of the electromagnetic signal. But apart from that, everything else can be very nicely connected. So we looked at what types of systems could be detected with both methods. So the blue here, so this is total mass of the binary and period for binaries that have different inclination from edge on, which is the best case scenario, to more inclined. And the blue is what we could detect with electromagnetic surveys if the signature was the relativistic Doppler boost. The purple lines are what we can detect with gravitational waves given different sensitivities. So this is the 11-year data set by nanograph. Projections we have for 2025 with IPTA and projections 10 years in the future. So you can look at our current, let's say, sensitivity. We can only do multi-messenger observations for the most massive binaries that are relatively nearby. But as the sensitivity of PTAs increases, you can see that the parameter space here expands. And we can do joint observations for more and more binaries. I just want to say that this is one of the many possibilities that we can explore in terms of multi-messenger science. This is a figure from one of the nanograph white papers we wrote for the decadal survey, where we summarize all the questions and all the signatures that we can explore in this decay. If you're not very familiar with this white paper idea, so in the US, every 10 years, the astronomical community comes together, writes these short white papers on each person on their favorite topic, and that sort of defines the priorities for the next decade. And in fact, multi-messenger and time domain astrophysics is one of the 3 top priorities for the US. So I think we will learn a lot in the 2020s about multi-messenger. So just to summarize the, let's say the top component, and I will go to the, very briefly at the notebook I prepared. As you probably all know, supermassive black hole binaries are formed in galaxy mergers, and they should be very common. We have these time domain surveys now that allow us to search for quasars with periodic variability, and we have quite a few candidates. It's very hard to confirm that these candidates are indeed binaries, and we have a lot of, we are doing a lot of work to combine different wavelengths and look for different signatures. And of course, the same binaries are this promising sources for gravitational waves and pulsar time arrays. And as I showed you, there's a part of the parameter space that we can probe binaries with both messengers. So I will stop here to see if you have any questions. And then I can move very briefly to the notebook I prepared. Okay, so I'll move to the notebook then. So what I will do, I know we bombarded you with information today, so I will just walk you through a few of the main ideas that we use in this type of signal processing. And I have throughout things that you could do if you're interested. So what I will do, I will just go through the notebook, and then if you guys want to spend more time and you have the energy to do some of the activities, feel free. Otherwise, we can call it a day. So, as I already mentioned, in this method, we work with light curves. And light curves are a collection of data points which show the evolution of the brightness over time for a source. In our case, the source will be a quasar. So typically when you get the light curve of an object, you will have a timestamp when the data were taken. You will have the brightness, which is expressed in magnitudes. And I think, I assume that you are a physicist and you have not taken astronomy classes, so I wrote the magnitude in terms of flux. That's what Sophie was asking before. And then you will have a measurement error for each of the observations. This will also be expressed in magnitudes. And then in general, you will have additional information, which is either quality flags about the conditions of the night that the data were taken, the pipeline, how well it worked, and so on. So here, I put together some of the places where you can find time domain data. For example, ZTF is one of the ongoing time domain surveys. You can select the most recent data release. Let's see if it works. Okay. We can do a search for an object, define the error radius around this input coordinate, and then we can run a query here and get the data. So here we see that we have 5 objects around this source where we looked. We can select one. This database has this very nice tool that you can directly look at the light curve. So, so this is how a light curve that you export from a database will look like. So it will have a lot of information about the time the observations were made, magnitude error, the filter, coordinates, some statistics, and so on. And then ZTF even gives you the images that you can look if you're interested in that part. There are I won't go to each of the databases. The way they work, some are more user-friendly, some are not. And that depends on how much money they spend on building these databases. And Catalina, for example, is a public database that you can only query up to 100 objects at a time because they are limited computationally. Same, and also the surveys, they're different in like how often they take observations, how deep they go, and so on. So if you want to play with the databases, I give you one of the most promising candidates, which is this candidate PG1302. I give you the coordinates and you can go to the different databases and download the data. I have done that already for you, so I have already put in the GitHub a couple of data files. And here's how the light curve will look like. The first one is the one that was published in 2015. And then I extracted another 3 years of data from another survey. One thing to keep in mind is that when you have different surveys, you possibly have different filters. For example, Catalina looks at unfiltered optical light. ZTF or PTF, they look at narrow band filters, like for example, red color, blue color, so on. So you have to be careful on how to calibrate this data. And that can introduce problems. I did the very simple brute force, taking the part of the light curve that is common to two and bringing the two light curves down. But if you talk to people, to AGN people, there's a lot of subtleties that you need to care when you're doing these type of things. So this is one of the candidates. And now I will tell you a little bit on how we can search for periodicity. And in general, we can take a periodogram, which is practically the an estimate of the power spectral density of the time series. The problem with astronomical data is that we typically don't have continuous observations. The only case we probably have continuous observations is maybe LIGO or I don't know, Kepler and some X-ray instruments. So most of the time in astronomy, we have sparse and gappy data because our source will end up behind the sun and we cannot observe it. We have weather, so we will have clouds and other stuff that will not allow us to open the dome of the telescope. We have instrument failures, maybe we cannot rotate the filter. Something goes wrong and we don't have data continuously, and that's unavoidable. But that's all astronomy, and we have the tools to work with that. So in searching for periodicity, the most established method is this Lomskarto periodogram. And what in practice it does, you specify an array of periods or frequencies that you want to search, and it fits the data with sinusoids of this period. So here I simulated some idealized sinusoids that you will see in a moment. And then I defined the frequencies for this periodogram. There are some limitations at what frequencies you can look. For example, the minimum frequency is defined by the baseline of the light curve. So that's probably something you've already heard for how we are doing the PTA analysis. Typically, and that's something we already discussed, maybe you need multiple cycles, and this is a mistake here. So if you need multiple cycles, you probably need to divide this minimum frequency by the number of cycles that you require. And then the maximum frequency can be defined by the sampling rate. There's a quantity called the Nyquist frequency. So if you take the average sampling rate, that is roughly the maximum frequency you can probe. In reality, in these periodicity searches, we didn't care about periods that are less than 30 days or 60 days, or even in the Graham and 2015 paper, I think the limit was 400 days. Because we don't expect that we will have many binaries at the very short periods, so we can limit the range that we search. So once we define the frequencies that we want to explore, we can just take this Lomskargel function, which is from the AstroML package. I think Steve suggested that you download and install this package. And here's, for example, my idealized simulation of a not very noisy sinusoid and how the periodogram will look like. We have sort of a delta function at the injected period. And you can play with this, like change. I'll see if my notebook is live now. And you can see that, for example, if I don't have that many cycles within my data, my periodogram will look somewhat different. Still, I get the same, the correct period. And now I want you to keep this figure in mind. And instead of having this idealized grid of observing every 5 days and so on, I will use the sampling pattern of this object. So I will just sample a sinusoid on top of during the observations that times of this. And you will see it will look something like that. I still get a major peak at the injected period, but I also get other peaks where I shouldn't have anything. And this effect is called aliasing, and it's a big problem in analyzing this type of data. And as a to-do, if you're interested, you can go ahead and sample at the observed times of PT1302, something like the period of PT1302, and see where you would get these other frequencies. Now, I'll just take a moment to explain what aliasing is. So here I have this signal, which you can see it's nothing. So we shouldn't get any peak at the periodogram, right? Now, remember, I told you that the Lomskargel just fits periodograms. So let's do this thing. You can see that I can fit a sinusoid even at this like 0 magnitude time series. And I can fit more sinusoids here. And I think you get the point. That's how I get the false peaks. Practically, I don't have enough information. I'm not taking data at the rate that I need. And for that reason, I can get fake peaks. Another thing that probably you want to know is, okay, I detected the peak in the periodogram. How do I know if this is noise or if this is something important? And there's a lot of literature on how you can do it when the assumption is white noise, which is most of the cases in astronomy. So what you can do is keep the timestamps fixed, and then scramble the magnitudes. So by doing this, you will get the false peaks from the sampling pattern, and then you will see if you get peaks of the same height just from the noise. For quasars, that cannot that's not the case, because the noise we have is correlated. And I will jump ahead a minute and show you what correlated noise means. So if we are here, and it's similar to how the stock price markets change. So we have stochastic variability. If we are here, it's, let's say, Wednesday today at 4. The Google stock closed at 150. Tomorrow, we expect that the price will be around that value. Might be 145, it might be 155. It's very, very unlikely that it will be 0. But in a year or 10 years, you cannot predict what this is. So in the short term, you can predict where this magnitude in this case or the stock price will go, but this information is not translated in the long term. How does this look if we look at the power spectrum? So we have red noise for high frequencies. So the power spectrum density goes as 1 over f squared. And for the low frequencies, the long-term variability, it's flat, it's white noise. And then I give you this function where you can use the sigma and tau. These are the two parameters that define the power spectral density here, and make different quasar light curves. So you can play with that. For example, we can change tau here, and you will see the variability gets different. We have something short, it becomes more erratic, and so on. And as a to-do, I have a few things that you can try. You can simulate different time random walk light curves, take their periodograms, and assess the false alarm probability of PG1302. If you go at this paper here, there is a table of all the different papers that looked at the time random walk parameters of PG1302, and you can see there's no agreement within the values. So that makes it even more complicated. And another thing you need to keep in mind is that typically select these sources from a very large sample. And in that case, we have what is called the look elsewhere effect. So for example, I was talking to Andrew and Jessica that were calculating the false alarm probability. If you want to assess or reject the hypothesis that your signal is consistent with noise at 1% level, you have to simulate, let's say, 100 light curves, and not one of them will have a peak as strong as the one you care about. But if you look at 1,000 objects, you need to increase the number of simulations by 1,000 to account for the trial factor. In quasars here, it's even more complicated because you're looking at the localized effect. So you cannot compare the high frequencies with the low frequencies. So you need also to take into account how many frequencies you have explored, which is not trivial always. And then you need also to increase the number of simulations, and that will give you the false alarm probability. So I will just end here, see if you have any questions. And of course, you can always feel free to get in touch with on Slack or email if you want to play with this and you have questions. Any questions? I'll stop sharing. I think unless you want to play with the notebook, we are done for the day. And
So you have one question, you mentioned that scrambling doesn't really work well for sensitive also on probability. Does that still apply to bootstrapping as well, or just bootstrapping? I heard bootstrapping very over.
so what are you thinking when you mentioned bootstrap? What are you thinking? What do you have in mind? Removing one point at a time?
Yeah, essentially, which is, I guess, is a little more jackknife, but still, like that would that work a bit better, or else even removing like chunks of data at a time?
I think removing chunks of data could work. You lose some of the information in the correlations. I think that's one of the important stuff. You really need to keep these correlations into your final periodograms and your analysis. And there's a lot of discussion on how you actually properly simulate this stochastic light phase. There's a lot of complications, and people, especially people who think about X-ray red noise on quasars, there's huge literature on that. Okay, so I think we can close the Zoom. Stephen Nihan are at the call right now, so for the people online, we will just close the Zoom. Thanks for staying with us until now, and we'll see you tomorrow.